Hi everybody, today I'll be presenting on the invasive meningococcal disease vaccine. So what is meningococcal disease? Well, the causative agent is a gram-negative bacterium called Neisseria meningitidis, and it's actually a commensal organism that lives within the human body. There are 6 common serotypes, A, B, C, W, Y, and X, that are the ones known to cause disease in humans. And the disease actually occurs when you have the bacteria that are residing within your body, and they actually invade into your brain or your blood. And so that brings us to the 2 common diseases that are types of meningococcal diseases, and that would be meningitis and septicemia, or also known as sepsis. So meningitis is actually just an inflammation of the uh, meninges of the brain and the spinal cord. So that's just your protective covering for your brain and spinal cord. And that's also where a lot of the blood vessels reside, so you can get blood flow to your brain. Common symptoms are fever, headache, stiff neck, nausea, and vomiting. Pretty standard there. And then septicemia is just blood poisoning by bacteria. So what happens with that is when you have the bacteria into your bloodstream, what they'll do is they'll eat away and degrade your blood vessel cell lining, and that'll allow blood to leak out of your blood vessels and form they'll leak out into your skin and organs, and that's not good, obviously. But some of the symptoms of that: fever, chills, fatigue, vomiting, muscle aches, diarrhea, and a purple rash. You get the purple rash because that's where the blood is coagulating and gathering up as it's leaking out of your blood vessels. Now, both of these are fatal. They can be fatal within a matter of hours, but with the proper treatment and preventative measures, that those fatalities are decreased a lot, way more than if you were not vaccinated or you didn't catch it in time. So, who's the number one offender for transmitting meningitis and other meningococcal diseases? Well, it's actually college students. Through practices like kissing or other stuff like that, they're able to transmit these bacteria from their nasopharynx into another person through their saliva, and so that's why we need to abide by a no PDA rule on college campuses to prevent the transmission of this disease. So transmission, like I just stated, it's transmitted by the saliva when you're kissing someone through very close contact, or it can be lengthy contact without kissing, just in close quarters, for example. It's actually less contagious than the common cold. Fun fact, actually. But you can also have patients who are actively infected and have disease, or you have asymptomatic carriers where the bacteria are still operating under a commensal, relationship to us, and they're just they're up in your nasopharynx hiding out, and they're not invasive yet. And that is, like I said, college students, they're the carrier rates are the highest in adolescents and young adults. And then, so you got risk factors. First one is age. The most susceptible to this disease are actually babies and young adults and adolescents. Excuse me. And also those who have complement deficiencies, so that they can't produce certain proteins for the complement activation. Also those who use complement inhibitors as well. There's drugs out there that inhibit complement activation, and that can also put you at risk. Also the HIV infected. Those who have to travel to endemic regions like Africa or Asia, where meningitis is more prevalent among the population. That's why the U.S. Tries to promote getting vaccinated before traveling to those countries. Like I said, college students are pretty susceptible to it, and then as well as military recruits for the same reasons as college students. They're living in close quarters, and you can have that lengthy contact just living pretty closely to someone. So here, I just wanted to show a diagram from the World Health Organization of the common serotypes that are found within regions of the world. The most notable ones are the sub-Saharan African meningitis belt right here. They have CWX. They also have the highest rates of meningitis in the world. It's probably close second behind them is Asia over in China and here in Australia. And as you can see, there's the B serotype is pretty standard across the entire world. C, W, X, Y, those all vary from region to region, and those are usually not like the everything like C, W, X, and Y are usually found in adults, or sorry, in not adults, infants, whereas the B serotype is found among the young adults and the adolescents. So, how do you prevent or treat this disease actually? So, prevention is accomplished by your subunit vaccines. All these vaccines that you see here in Table 1, they are all subunit vaccines that, excuse me, that are polysaccharide vaccines or conjugate vaccines. And the reason why they are like this is because the bacteria is a gram-negative, so it has two membranes with an intermembrane space, and then the bacterial capsule. And the polysaccharide vaccines attack like A, C, W, Y because they attack a certain they incorporate certain parts of the polysaccharide capsule in the vaccine, and that's how your body knows to attack those cells. However, you will notice that meningitis B, any vaccines with the B serotype are separate from A, C, W, and Y for a different reason, because there's actually the polysaccharide is so similar in humans that you actually would promote a self-response if you try to put those polysaccharides from the B serotype in the vaccine. Your body wouldn't know what to do with it because it would just think it was attacking itself. But that's for a little bit later on. And then treatments, once you are infected, is just antibiotics because since it is a bacteria, that works pretty well. So here in the U.S., there are several approved vaccines. Your ACWY vaccines are Menactra, Menveo, Menquadfi, excuse me, and those have been licensed, in 2005, 2010, and 2020. So those are all pretty recent, actually. And then you move on over to your meningitis B vaccines, Trumenba and Bexsero, both of which have been licensed and have been in the works since the early 2000s, once the B serotype was becoming more prevalent across the world and causing more disease. And I put Table 1 here from this source, and I just wanted to point out that this is the Bexsero vaccine, the four-component meningitis B vaccine. And I just wanted to give you a first glance of what's actually in here. So you have OMV, which is your outer membrane vesicle, an adhesion protein, and another protein, and this is a factor H binding protein, and that's a Necessaria binding adhesion thing. It's another protein. So that brings me to the vaccination schedule for infants, toddlers, and young adults. For infants, 2 to 5 months of age, 6 to 11, it doesn't really matter. They're all pretty similar. You have at least a couple doses with a 1 month interval between those doses. You can get boosters after the primary schedule is done. But also for infants and toddlers, you can also combine vaccines, you can combine Bexsero with hepatitis B, MMR, so you can get multiple vaccines done with the same shot. Just makes it easier on the babies. So then young adults, 16 to 23 years of age, is the acceptable age range for getting this vaccine. However, most physicians actually would like between 16 and 18 to be the preferred range. Since a lot of kids are going off to college, they'll usually just get it done right before then. I know I got one done. I got a meningitis vaccine before I had to come here to UD. And I had the same 2 doses with a month interval between those doses. It's, and I haven't had meningitis yet. So that's a really great thing, actually. So here's where we get into the meat of things. So there are a lot of those vaccines that I showed you earlier have all been developed over the course of 20 or 30 years. And the Bexsero one and the other meningitis B vaccines have really been able to be formulated using this technique, reverse vaccinology. And what happens here is you use bioinformatics to define the genome sequence of the pathogen, and then you use some computer algorithms to help predict the antigens for the new vaccine. And so, like I said earlier, you have in Bexsero, you have 1/4 of OMV, 1/4 of the adhesion protein A, 1/4 of NHBA, and 1/4 of the factor H binding protein. So factor H binding protein is just a lipoprotein that is an effective inhibitor of the alternative complement pathway. You have NADA, it's just an adhesion protein binding bacteria to the human epithelial cells, and so that's how they're able to bind in the blood or in the meninges. Then you have heparin binding antigen, which is NHBA. So that was the one I messed up on earlier. But it's a lipoprotein that promotes resistance in the blood, which is why you have septicemia as a disease resulting from this bacteria because of that antigen right there. And so basically this whole approach, the reverse vaccinology, the result of this was meningitis B4C, also known as Bexsero. And here is the exact list of all the ingredients inside the vaccine. So you got 50 micrograms of each of those proteins or antigens. You have an outer membrane vesicle from New Zealand. That was just added for coverage reasons. So not it's going to protect you against from some antigens from A or C or X or W or something like that. And you have aluminum hydroxide as an adjuvant, sodium chloride, histidine, sucrose, and water. And those are all the components that make up that Bexsero vaccine. So serotype B is the most frequent causative agent of meningitis in the world, actually, right now. And like I said earlier, polysaccharide vaccines will not work against meningitis B. And that's because the capsule has alpha 2A linked di and triacyllosyl units, which is identical to some human polysaccharides. So you can't use that to develop a vaccine against meningitis B because you'll be introducing self-harm. And just for a little quick history, Cuba, Norway, Chile, New Zealand, and the Netherlands have all developed their own outer membrane vaccines when they experienced epidemics in the past to combat meningitis B. And so this diagram here, it's just here to show you what proteins or antigens are present. So you have your NADA, your NHBA. Here's a porin A. It's just a different protein that can be attacked as well. And then you also have as well RMP, OPA, porin B, and then lipopolysaccharides. These are all components that are present in that bacterium. And so the research against serotype B has been focusing on targeting these subcapsular antigens below the capsule here, outer membrane vesicles they're vesicles that bud off from this outer membrane here, and individual antigens themselves. So like I said, POR A, POR B, OPC, OPA, NSPA, those are all present in this outer membrane as well. So to develop the vaccine for the OMV vaccines, you had to do detergent elimination to eliminate these toxic lipopolysaccharides to be able to develop OMV vaccines. And OMV issues, resolutions, this is not the same as Bexsero. This is a slightly different version. It's not based off of the B, it has a different effect. But single POR A containing OMV vaccines, they provide limited coverage. They're only useful in an epidemic with one strain, usually. The outer membrane proteins and the exposure of the epitopes by detergent extraction, alteration can occur, and this explains why there was absent responses in children when the Cubans developed their vaccine. The Dutch solved a toxicity problem. They eliminated the detergent extraction by disabling this gene, LPXL1, and that attenuates the endotoxins while preserving the adjuvant activity. So basically, you won't have any toxic side effects from these lipopolysaccharides. And then finally, the ability of these proteins to undergo antigenic shift or gene deletion means that immunity that is gained quickly fades away, and so you just have to get more shots. But that's all been addressed and has been fixed with the new vaccines that we've produced, like